Welcome to another episode of My Weird Prompts, an AI-generated podcast featuring the random prompts of Daniel Rosehill as answered by a revolving cast of friendly AI characters. Join us for deep dives into AI, technology, and whatever other random thing Daniel finds fascinating today. Subscribe on Spotify or your favorite podcatcher. Now, today's episode.
This episode was generated using artificial intelligence. Please verify facts.
Hey Herman and Corin. So I said that I would love to do an episode in which I provide the Homefront Command guidelines for rocket shelter here in Israel. And that is an idea, but I actually thought, I'm listening to your excellent episode about what to do during if you happen to have a toddler or you're pregnant. And I have to say, every episode of this podcast is an education. Even though I've been living here in Israel for many years, a lot of what I learned, I wasn't even aware about. I do recall actually hearing about the reinforced delivery rooms, but it's excellent to know if someone were to find themselves in that situation. Great overview. You talked in an episode about the Homefront Command guidelines regarding the order of precedence. If you can get to a public shelter, if the alert goes off and you have 90 seconds in Jerusalem, to give an example. And as you pointed out, if you don't have a mamad in your apartment, as we don't, and as many people don't, then you're right, that window of opportunity is extremely narrow. More realistically, based on our experience in the previous Iran war, was more like a window of 10 minutes to 7 minutes, because that was when these early alerts went off, and it's still very tight, especially if, as happened, you get alerted at 3 a.m. and you've already been alerted 4 or 5 times that day. This happened so many times, so you're just literally in the dead of the night, woken up from sleep. Now the countdown starts. So what I'd love to chat about, Herman and Corin, in this episode is, let's put the Homefront Command guidelines on pause for the moment, because they are based on an understanding of science that I presume is quite good, but it may not be necessarily perfect. They have specific guidelines regarding where to shelter if you have to shelter in your building, and it's based on the floor. If I recall, there's specific floors above you, below you, and you should try to be somewhere in between, and you don't want to be near a window. They also have guidelines regarding if you have to shelter in your apartment, which is kind of an apartment without a safe room, which is, let's say, the last resort, or the least ideal situation. You can't get to the stairwell. Think about maybe someone with mobility issues or someone very elderly, and they can't even make it out to the stairwell. So the best they can do is to get somewhere in their apartment. They have even guidelines about which rooms can't be considered last resort rooms. And all these guidelines are there basically based on the threat estimations for where would be the most and least safe from a rocket, shrapnel, and then secondary damage in the building. So Herman and Corin, I'd love to ask you about the whole structural engineering of this. We're considering basically the stability of buildings and where the safest part of a building is going to be, regardless of exactly which floor we're talking about. I think it might be more helpful to actually look at this a step back, such that if we are going into a building, or the 90 seconds, for example, if you can, I can recall from the guidelines that if you can make it to a public shelter and you don't have a mamad, that's what you do. If you're in the street, which happens, if you're out in the open and there's nowhere to go, you put your hands over your head, and you see this happen in the highways or the people driving. But if you're in an urban area and you can make it into a building, but not the public shelter, you make it into a building. And then you have to figure out where's the safest part of that building. So Herman and Corin, let's talk about that triage process, because it could be really life-saving potentially. If you are doing that, let's imagine the siren goes off, you find yourself in a street, you can't make, you know that the nearest shelter, you're not going to make it there in time. So you're looking around. You're in Jerusalem or you're in downtown Tel Aviv, you see a few buildings. Within the buildings, you've got a choice of floors. This isn't, the doors are open, let's say. Where do you go from here? How would you size up the best building to shelter in, and finding the safest part of that building if one had to go to that resort? Herman and Corin, I know these episodes are very detailed, but I think they're also very important. So we will continue. Let's hear your advice about this eventuality.
Hey everyone, welcome back to another episode of My Weird Prompts. We are coming to you from Jerusalem, as always, and today we are getting into a topic that hits very close to home for us. It is February 22nd, 26, and if you have been following the news or living here in the Levant over the last few years, you know that our living situation often informs the kinds of things we think about. Today's discussion is really grounded in the practicalities of our environment, but it is also a deep dive into the physics of the world around us.
Herman Poppleberry here. And yeah, Corin, this is one of those topics where my inner engineering nerd and my everyday survival instincts really start to overlap. We have had a few quiet months, but the reality of urban life in a conflict zone means you are always subconsciously scanning the horizon. Today's prompt comes from Daniel, who wants to know about the structural engineering and stability of buildings to determine the safest places to shelter during a siren. Specifically, if you are in an urban area like Jerusalem or Tel Aviv and you cannot reach a public shelter or a dedicated safe room in time, how do you evaluate the buildings around you on the fly?
It is a sobering topic, but a vital one. We have talked about the Home Front Command guidelines before, but Daniel's prompt pushes us to look deeper into the why behind those rules. Why is one floor better than another? Why does the material of the building matter? If you are standing on a street corner and the siren starts, you have maybe 90 seconds in Jerusalem. In Tel Aviv, it might be 60. If you are further north or south, you might have 15 seconds or even less. That is not a lot of time to make a decision that could save your life.
Exactly. And that decision should not be based on a guess or a gut feeling. It should be based on an understanding of how buildings are put together. When we talk about structural engineering in the context of a blast or a rocket impact, we are looking at how a structure handles extreme, sudden loads that it was not necessarily designed for in its daily life. Most buildings are designed for gravity and maybe some wind or seismic activity, but a blast is a whole different animal. It is a dynamic, high-velocity event that tests the very limits of material science.
So, let us set the scene. You are out for a walk, maybe near Zion Square in Jerusalem or on Rothschild Boulevard in Tel Aviv. The siren goes off. You realize you are not going to make it to a designated public shelter, which we call a miklat, or a fortified safe room, what we call a mamad, in time. You see 3 or 4 different buildings nearby. Herman, what is the first thing you are looking at from a structural perspective?
The very first thing I'm looking at is the age and the material of the building. In Israel, there is a massive divide between buildings built before the early 1990s and those built after. In 1991, after the Gulf War, the building codes changed significantly. Any building built after that is required to have reinforced concrete safe rooms. But even if you cannot get into one of those rooms, the entire skeleton of a newer building is generally much more robust.
So, newer is better because of the reinforced concrete skeleton?
Generally, yes. In older Jerusalem buildings, you see a lot of masonry, a lot of Jerusalem stone. While that looks very solid, it is often what we call load-bearing masonry. That means the walls themselves are holding up the weight of the floors above. If a blast damages a significant portion of a load-bearing wall, the whole structure above it can become unstable very quickly. In a modern building, you usually have a reinforced concrete frame. The walls you see from the outside are often just infill or cladding. If one of those panels is blown out, the skeleton of the building remains standing.
That makes sense. It is the difference between a house of cards where every card is vital and a steel cage where you can knock out a few bars and the cage stays upright. But let us talk about the specific location within the building. The guidelines always say to go to the stairwell. From an engineering standpoint, why is the stairwell the gold standard?
The stairwell is essentially the spine of the building. In almost all modern construction, and even in many older apartment blocks, the stairwell is designed as a vertical concrete tube. It has to be incredibly strong because it carries the heavy load of the stairs themselves, and it often acts as a shear wall. A shear wall is a structural element used to resist lateral forces like wind or earthquakes. Because the stairwell is a continuous vertical shaft of reinforced concrete, it is often the most rigid part of the entire structure. It is designed to stay standing even if the rest of the building is swaying or taking damage.
And because it is in the center of the building, you have the added benefit of mass between you and the outside world, right?
Precisely. This leads into what engineers call the rule of two walls. When a blast occurs, you have two main threats: the primary blast wave, which is a high-pressure wave of air, and fragmentation, which is shrapnel or debris flying at high speeds. Every wall between you and the exterior of the building acts as a filter. The first wall takes the brunt of the pressure and the majority of the shrapnel. If that wall fails, the second wall is there to catch what is left. By the time the energy reaches the interior stairwell, it has been dissipated by multiple layers of structural material.
I have always wondered about the floor choice, though. The advice is usually to avoid the top two floors and the bottom floor. Why is the ground floor considered less safe? I would think being close to the exit would be a good thing.
It seems counterintuitive, but think about the physics of a blast. If a rocket impacts the street or the area immediately outside a building, the ground floor is the most exposed to the direct line of sight of the blast. Also, many buildings in Tel Aviv and Jerusalem have what we call a soft story on the ground floor. This is often where you have parking or shops with large glass windows and fewer internal walls. From a structural engineering perspective, a soft story is a weakness. It does not have the same lateral stiffness as the floors above it, which are full of apartment walls. If the ground floor collapses, the whole building comes down.
And the top floors? I assume that is because of the risk of a direct hit on the roof.
Exactly. The roof is a large, flat target. If a rocket hits the roof, it does not have those two walls of protection we talked about. You only have the roof slab itself between you and the impact. There is also a phenomenon called roof slapping, where the pressure wave from an explosion can cause the roof slab to flex violently, potentially causing it to detach from the walls or collapse inward. By staying at least 2 floors below the roof, you are putting multiple concrete slabs between yourself and a potential roof impact.
So, if you are in a 5-story building, you want to be on the second or third floor stairwell.
Spot on. You are high enough to be away from the ground level blast and debris, and low enough to have a few layers of concrete above you.
Let us talk about Jerusalem specifically for a second. We live here, and we see these beautiful old stone buildings everywhere. Some of them are over 100 years old. If I am in Rehavia or Naklawat and a siren goes off, and I see one of those classic old stone houses versus a modern 3-story apartment building, even if the modern one looks a bit flimsy, you are saying the modern one is the better bet?
In most cases, yes. Those beautiful old stone houses are often built with thick, heavy walls made of stone and mortar. While they have a lot of mass, they lack ductility. Ductility is the ability of a material to deform without breaking. Reinforced concrete is ductile because of the steel rebar inside it. It can bend and absorb energy. Old stone and mortar are brittle. If they are hit with a shock wave, they tend to crack and fail catastrophically. Plus, those old buildings often have wooden floor joists rather than concrete slabs. If a wall fails, those wooden floors have nothing to hold them up.
That is a really important distinction. The mass of the stone gives you a false sense of security. It might stop a piece of shrapnel, but it might not stop the whole wall from falling on you if the foundation or a corner is compromised.
Right. And speaking of Jerusalem stone, we have to talk about cladding. Most modern buildings in Jerusalem are required by law to be faced with stone, but this is not load-bearing stone, it is just thin slabs attached to the concrete frame. In a blast, that stone cladding can actually become a secondary hazard. It can peel off the building and turn into huge pieces of flying debris. So, even if a building looks like a fortress because it is covered in stone, you have to remember that the real strength is in the concrete skeleton underneath.
Okay, so let us move to Tel Aviv. Different architecture, different risks, lots of glass, lots of Bauhaus-style buildings with those open pilatus or pillars on the ground floor. What are the specific engineering red flags there?
Glass is the #1 enemy in an urban blast environment. In Tel Aviv, you have these beautiful modern buildings with floor-to-ceiling windows. If you are evaluating a building in 90 seconds, stay as far away from glass as possible. Even if you are behind a wall, if that wall is adjacent to a large glass facade, the glass can shatter and fill the interior space with high-velocity shards. The Bauhaus buildings with the open pillars on the bottom are a classic example of the soft story problem I mentioned earlier. If you are in one of those, you definitely want to get up into the stairwell and away from those ground floor pillars.
What about the idea of the inner room? If you cannot get to the stairwell, the advice is usually an inner room with as few exterior walls as possible and no windows. How does that work structurally?
It is the same principle of energy dissipation. An inner room, like a hallway or a bathroom, is typically surrounded by internal partition walls. While these might not be load-bearing, they still provide a physical barrier. If you are in a room with no windows, you have eliminated the biggest risk of injury from flying glass. From an engineering perspective, you are trying to find the point in the building with the highest density of vertical elements. Usually, that is near the center where the plumbing stacks and internal walls congregate.
I remember reading something about the way blast waves move through buildings. They do not just hit the front and stop. They can wrap around corners and move through hallways. Does the shape of the building matter?
It absolutely does. This is where fluid dynamics meet structural engineering. A blast wave behaves a bit like water. It will flow through any opening like a window or a door, and it can actually gain pressure as it is funneled down a narrow hallway. This is why you never want to stand directly in line with a doorway or a window, even if you are in an inner room. You want to be tucked into a corner. Structurally, the corners of a room are also stronger because that is where two walls meet, providing more rigid support.
So, if you are in that inner room or the stairwell, you should sit down against an internal wall, below the window line, obviously, and away from the door.
Exactly. And if you have the choice, lean against a wall that is perpendicular to the most likely direction of a blast. If a wall is hit head-on by a pressure wave, it is more likely to flex or fail. A wall that is parallel to the blast wave is under less direct stress.
That is a level of detail I think most people do not consider. You are not just looking for a wall, you are looking for the orientation of the wall.
It is hard to do that in 90 seconds, of course, but the general rule of thumb is get to the center, get low, and stay away from openings.
Let us talk about the worst case scenario. We've seen images of buildings that have taken a direct hit. Sometimes the whole building stays up, and sometimes a corner collapses. What determines that kind of structural resilience?
It comes down to redundancy. In engineering, redundancy means having multiple paths for a load to travel through a structure. If one column is destroyed, can the beams above it transfer the weight to the neighboring columns? This is called progressive collapse resistance. Modern buildings are designed with this in mind. They use something called tie force requirements, which basically means all the structural elements are tied together so strongly that if one part is removed, the rest of the building can bridge over the gap. Older masonry buildings have almost zero redundancy. If you take out a chunk of a load-bearing masonry wall, there is nothing to bridge that gap, and the weight of everything above it just pushes down until it collapses.
So, when you are looking at a building, you are essentially looking for signs of redundancy. A building with a lot of visible columns and a clear repetitive structure is probably more redundant than a building that looks like a single solid block.
Generally, yes. Also, look for the quality of the construction if you can. It is hard to see the rebar, obviously, but you can see the condition of the concrete. If a building is crumbling, has exposed rusted rebar, or deep cracks in the structural elements, its ability to handle a sudden blast load is significantly compromised. Rusting rebar is a huge red flag. When steel rusts, it expands, which causes the concrete around it to pop off, a process we call spalling. This weakens the bond between the steel and the concrete, which is where all the strength comes from.
That is a great tip. Even in a hurry, you can spot a building that has been poorly maintained. If you see chunks of concrete missing and brown stains from rusted metal, maybe pick the building next door.
Exactly. Maintenance is a proxy for structural health.
I want to go back to the stairwell for a second. You called it a tube. Is there a risk of the stairs themselves failing? If the building shakes violently, could the stairs detach and leave you trapped?
It is a possibility, but stairs are usually anchored very deeply into the floor slabs and the walls of the stairwell. In a modern reinforced concrete building, the stairs are often cast at the same time as the floors, making them one continuous piece of stone and steel. They are incredibly tough. The bigger risk in a stairwell is actually not structural failure, but smoke or fire if the building is hit elsewhere. But for the immediate 90 seconds of a siren and a potential impact, the stairwell remains the safest structural bet.
What about the elevator? I know the rule is never to use the elevator during a siren, but what about the elevator shaft? It is also a concrete tube, right?
It is, but you do not want to be anywhere near it. First, the elevator itself can become a piston in a blast, moving unpredictably. Second, the doors of an elevator are relatively thin metal and offer very little protection compared to a solid wall. And third, if the power goes out or the building shifts, you are trapped in a very difficult place for rescuers to reach. The stairwell gives you protection plus a clear path for evacuation or rescue.
That makes total sense. Now, let us think about the street level again. You are in a dense urban area. You see a parking garage. Usually, those are all concrete. Is a parking garage a good place to duck into?
Parking garages are interesting. They are usually very heavy reinforced concrete structures. However, they often have very few internal walls. It is a lot of open space. This means a blast wave can travel a long way through a garage without losing much energy. Also, you have the risk of cars. Cars are full of fuel and glass. If you do go into a parking garage, try to find a corner where there are thick concrete walls and stay as far away from the parked cars as possible. And again, avoid the very lowest level if it is partially open to the street.
So, the garage is okay if you can find a solid concrete nook, but it is not as good as a residential stairwell with multiple internal walls.
Correct. The residential building has more internal complexity, which is what you want for breaking up a blast wave.
We have talked a lot about what to look for, but what about what to avoid? Besides glass and soft stories, are there any other architectural features that should make us run the other direction?
Overhanging elements, balconies, large decorative cornices, or heavy signage. In a blast, these are the first things to be shaken loose. You do not want to be standing under a beautiful stone balcony when a shockwave hits the building. Also, stay away from areas with a lot of utility infrastructure. You do not want to be near gas lines, large electrical transformers, or heavy water tanks on the roof. In many older buildings in Israel, you see those large solar water heaters on the roofs. If those are dislodged, they are essentially heavy metal drums full of hot water falling from the sky.
That is a terrifying thought. So, you are looking for a building that is clean, well maintained, and has a solid, simple geometry without a lot of bits sticking out.
Exactly. Simple is safer. Complex shapes create stress concentrations. A nice, boring, rectangular apartment block from the 1990s is actually a marvel of safety compared to a complex, artistic modern structure with lots of cantilevered sections.
It is funny how our perspective changes. Normally we would walk past those 1990s blocks and think they are a bit dull, but in this context they are beautiful pieces of engineering.
They really are. They were built with a very specific set of threats in mind, and they do their job remarkably well.
I want to touch on something we see a lot of lately. Tama 38. For those who do not know, this is the National Outline Plan for Earthquake Strengthening. You see these old buildings in Tel Aviv and Jerusalem, surrounded by scaffolding, where they are adding new floors and often a mamad to every apartment. From an engineering perspective, how does a Tama 38 building compare to an original old building?
Tama 38 is actually a huge win for safety in this context. The whole point of the program is to take an old, brittle building and give it a new, ductile skeleton. When they do a Tama 38 project, they are usually drilling deep piles into the ground and building a new reinforced concrete core, often the stairwell and the safe rooms that is tied into the old structure. It effectively anchors the old building to a modern, stable spine. If I had to choose between an original 1960s block and one that has undergone Tama 38, I would pick the Tama building every time. It has been retrofitted to meet modern seismic and blast standards.
That is good to know, because those construction sites are everywhere. It makes the city feel like it is constantly under renovation, but it is actually a massive upgrade to the urban resilience.
Exactly. It is a slow process, but it is transforming the risk profile of entire neighborhoods.
Let us talk about the aftermath of the siren. The home front command always says to stay in the shelter for 10 minutes after the siren stops. From an engineering and physics perspective, why is that 10-minute rule so important?
There are two main reasons. First, there is the threat of multiple launches. Just because the first siren stopped does not mean the threat is over. But the second reason, which is more relevant to our structural discussion, is interception debris. We have the Iron Dome and David's sling systems, which are incredible pieces of engineering. They intercept rockets in the air, but that energy has to go somewhere. The rocket and the interceptor are blown into hundreds of pieces of jagged metal. These fragments do not just disappear, they fall to the ground at terminal velocity.
And terminal velocity for a piece of heavy metal is no joke.
Not at all. A piece of shrapnel the size of your phone falling from several thousand feet can easily penetrate a roof or a car. It can certainly be fatal. The 10-minute rule ensures that all the debris from an interception has had time to fall and settle before you step back out into the street. From a structural perspective, your building is still protecting you from this vertical threat even after the horizontal threat of the blast wave has passed.
So, the building is a shield against the blast, and then it becomes an umbrella against the falling debris.
That is a perfect way to put it.
Let us talk about the physics of the blast wave itself. You mentioned it behaves like water. I've heard about something called the Mach-Stem effect. Can you explain that in layman's terms?
Sure, when an explosion happens near the ground, you get two waves. You get the incident wave, which travels directly from the explosion to the building, but you also get a reflected wave that bounces off the ground. At a certain distance, these two waves merge into a single, vertical wavefront called the Mach-Stem. This merged wave is much more powerful than the original blast wave. This is another reason why the ground floor is so dangerous. It is where the Mach-Stem is at its most intense. As you go higher up the building, the pressure actually decreases slightly because the waves have not merged in the same way.
So, the ground floor gets hit with a double wave. That explains why you see so much more damage at the street level in those photos.
Exactly. The physics of reflection and reinforcement can double or triple the effective pressure on the lower parts of a structure.
Okay, let us summarize the triage process for someone who finds themselves in this situation. You have 90 seconds.
Step 1. Look for age. If you can see a building that looks like it was built in the last 30 years, or one that has clearly been retrofitted with Tama 38, head for that one. It likely has a reinforced concrete frame.
Step 2. Look for mass and material. Avoid the old stone houses if there is a concrete alternative. Avoid anything with massive amounts of glass on the exterior. Look for a building with a simple rectangular shape.
Step 3. Once inside, find the stairs. Do not use the elevator, go to a middle floor. If it is a 5-story building, aim for floor 2 or 3. If it is a 20-story tower, aim for the middle floors, but make sure you are in the reinforced core.
Step 4. Position yourself. Get into the stairwell. Sit down against an internal wall. Stay away from any doors or windows and protect your head. If you can, pick a wall that is perpendicular to the street.
And if you absolutely cannot find a stairwell, find an inner room with no windows and as many walls as possible between you and the street. A bathroom or a hallway is usually your best bet.
What if you are in a really old area where everything is masonry, like the old city or parts of Naklao, where there are no modern buildings?
In that case, you are looking for the thickest walls you can find. Often, the ground floor of those very old stone buildings actually has the thickest walls because they had to support the weight of everything above them without the help of modern materials. In that specific case, where there is no reinforced concrete skeleton, the ground floor might actually be safer than the upper floors, provided you are not directly in line with a door or window. You want to be in a vaulted space if possible. Vaults are structurally very strong because they redirect the pressure into the ground.
That is a great point. The arches and vaults of ancient architecture were the reinforced concrete of their day. They handle pressure very well.
Exactly. An arch is always in compression, which is where stone is strongest. Stone has great compressive strength, but almost no tensile strength. An arch keeps the material in its comfort zone.
This is all incredibly practical, Herman. It is one of those things you hope you never have to use, but knowing the engineering behind it makes the guidelines feel less like arbitrary rules and more like a logical system. It takes some of the panic out of the situation when you have a mental checklist.
That is the goal. When you understand the load paths and the way energy moves through a structure, you can make better decisions even when you are under extreme stress. It is about reducing the variables of risk. You can never eliminate risk entirely in these situations, but you can certainly tilt the odds in your favor by picking the right building and the right spot within it.
It also makes me appreciate the building codes we have here. You realize how much thought has gone into the urban fabric of cities like Jerusalem and Tel Aviv over the last few decades. It is not just about aesthetics or density, it is about resilience. We are living in a place where the architecture is literally designed to keep us alive.
It really is. Israel has some of the most stringent building codes in the world when it comes to blast resistance and seismic safety. We are essentially living in a giant laboratory of structural resilience. Every time a building is hit and stays standing, engineers are looking at why and how to make the next one even better.
Well, I think we have covered the core of Daniel's prompt. It is a lot to take in, but the main takeaway is that the architecture around us is not just a backdrop. It is a shield if you know how to use it. It is about looking past the Jerusalem stone and the Bauhaus balconies to see the skeleton underneath.
Well said, Korn. And for our listeners, whether you are here in Israel or in any other urban environment, taking a moment to look at the buildings you pass every day through this lens is a good exercise. Where would I go? Which building looks the most robust? It is a bit of mental mapping that can make a huge difference if you ever have to make that 90-second decision.
Absolutely. Before we wrap up, I want to remind everyone that if you've been enjoying my weird prompts, we would really appreciate it if you could leave us a review on your podcast app or a rating on Spotify. It genuinely helps the show reach more people who might find these discussions useful. We have been growing a lot lately, and it is all thanks to you guys sharing the episodes.
Yeah, it makes a big difference for us. We love seeing the feedback and knowing which topics are resonating with you all. We have got some great prompts lined up for the next few weeks, ranging from the ethics of AI to the engineering of ancient cathedrals.
You can find all our past episodes, including the ones we mentioned about the Homefront Command and safe rooms, at myweirdprompts.com. We have a full archive there and an RSS feed if you want to subscribe directly. We also post some of the diagrams and engineering sketches Herman talks about on the site.
And if you have a prompt of your own or just want to get in touch, you can reach us through the contact form on the website or email us at show@myweirdprompts.com. We are always looking for new angles to explore, no matter how weird or technical they might be.
Thanks to Daniel for sending this one in. It is a heavy topic, but one that is very necessary for our context. We hope everyone stays safe out there and takes a moment to appreciate the engineering that keeps our city standing.
Stay safe, keep looking at the world with a bit of a curious eye, and we will talk to you in the next episode.
This has been My Weird Prompts. Thanks for listening. Goodbye.
Goodbye.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to another episode of My Weird Prompts, an AI-generated podcast featuring Daniel Rosehill's AI prompts, as answered by a revolving cast of friendly AI characters including me, Cornelius the Sloth. Subscribe on Spotify or visit myweirdprompts.com.